Okay, so am I audible? Yeah, guess. Okay, so discontinuous Galerkin method for the Navier-Stokes. So my background is not really FEM method. I have a bachelor's in mechanical engineering, but I shifted to applied mathematics. So I have worked in CFT, but only with the finite volume and lattice Boltzmann. That's what I was acquainted with. But it's only recently that I got acquainted with the finite element-based CFD side of things. And yeah, FEniCS was actually a good, it's the best way to implement my own weak formulations. Yeah, and this work that is presented here was actually done as part of a small project seminar module that we have in my master's course. So yeah, around 3 to 4 months were dedicated to this project, and yeah, good enough results were achieved. So what's with the CG and DG debate? Well, at least I can speak on behalf of the not the whole CFD community, but yeah, DG has its own benefits. Let's say on unstructured meshes, or yeah, with parallelizability, scalability, then mass conservation, and more specifically the last point, that is sharp gradients. So or shock solutions. So references are not a lot, so I thought I'll get introduce them to you in the beginning. So one of the book by Ralph Hartmann, Dr. Ralph Hartmann, he was from the German Aerospace Center from Aerodynamics and Flow Technology. He has written a wonderful book, which I was my main focus to get the literature from. So Navier-Stokes equation, I've just rewritten the convective terms, so it's easier to analyze the fluxes. What I did was I started slowly with the diffusion equation, implemented the DG method, studied and implemented DG method for that. Then slowly went on to the advection part, linear advection. Then also split it, get the convection diffusion, then again DG, and then FEniCS for that. Then Stokes. Again, there are new terms which are treated now, the pressure gradient and the velocity divergence terms. And then finally, we know then how to treat the individual terms, the diffusive term, the convective term, pressure gradient, velocity divergence terms. So we already have had 2-3 talks on continuous and discontinuous Galerkin, so maybe I'll speed up some of these parts. Well, we have a discontinuity at the element boundary, so this leads to a lot of additional terms in our weak formulations. Let's see. Because of this discontinuity, we have jumps and averages, which also were discussed in the talks. But something new, which I would like to say, a tensorial jump. So one of the most famous lemmas for discontinuous Galerkin is what is presented over here, where yeah, when we write the weak formulation over an element, when we sum up over all elements, we end up with a result where that's where we use the averages and the jumps. Just I'll get this also out of the way. The time integration method that I stuck to was a fractional theta scheme, which is not as widely used, but well, you split the time step into 3, and then you solve the equations in these intermediate steps before you get the final solution. So in a certain setting, this is unconditionally stable, and the other properties that you see with the values of theta and alpha. So that's how you split the steps. Within one step to get the final solution, you solve these equations. For Navier-Stokes, it would look something like this. So Poisson equation, simple thing. We have these additional terms. This was from continuous Galerkin case, but then we get these additional terms over here. Well, the choice of these penalty parameter, we penalizes a discontinuity, so we understand it better from the coercivity analysis. Simple, the implementation, and also FEniCS, we have all the options for averages, jumps. So it wasn't a problem to implement this in FEniCS. Simple equation which is done in it's a tutorial. Yeah, but the thing is, with visualization, I was hoping to have this doubt cleared, to not be able to see the discontinuous elements, which I can speak to for the founders here and maybe understand where I'm going wrong with the visualization, because it looks like the projection is onto the P1 space. So yeah, but does not affect the result. Uh, with the heat equation also, not a problem. Um, Again, with the linear advection, this is something what we would have in the continuous Galerkin case, but then we get the additional terms over here. This is something that corresponds to the upwind scheme that was discussed in the previous talks also over here. So implementing this also in FEniCS for a linear advection case, not a problem. Again, with the discontinuities, maybe with the visualization part, yes. Um, so just advection of a sine wave. Um, So since we know now how to treat the diffusion term and the convective term, uh, we could also now, I started slowly going forward with convection diffusion. Well, now here we can see the superiority of DG methods over the continuous Galerkin methods, where we would additionally require, for this to be stable, we would require some stabilization parameters like stream wind, upline SUPG, PSPG. But the discontinuous Galerkin, yeah, for advection dominated problems, we can see how it works well. So all this was for a scalar quantity, but I wanted to move on to a vector valued quantity, because since in Navier-Stokes we deal with velocity, vector valued quantity. So and then maybe convection diffusion, but for a vector valued quantity. So to treat the diffusion term would not be a problem. Again, it's just a straightforward implementation from the scalar valued case, CG terms, but then we have the additional terms which come up from the DG formulation. But then how to treat the convective term, again using the lemmas, not going much into derivation, but writing the final results here. Well, uh, we something from the CG case, but then additional terms over here. We end up having to come up with a choice for a numerical flux for the convective term. And well, widely studied flux is the Lax-Friedrich flux. But then we also have upwind. There are more in the literature. But yeah, Lax-Friedrich is most widely known. And also, I think people who are familiar with FEM, finite volume, also are aware of yeah, the Lax-Friedrich flux. So now for a vector valued U, one could be a viscous-Berger equation. Again, this also was implemented in FEniCS, compared against a continuous Galerkin tutorial. Yeah, there are no reference values, but the behavior was as we would expect it to be. Yeah, now maybe all this, we are already discussed convection diffusion, so maybe I just sped up a bit. But then the Stokes, now we are slowly moving on to Navier-Stokes. We know now how to treat the diffusion term with a SIPG method, but what to do with the pressure gradient and the velocity divergence terms. Again, using the same lemma, you write the weak formulation over an element, you sum up over all elements, then you have something that we have with the CG case, but then the additional terms over here. Now again, we would want to have a choice for what could be this the numerical counterpart for the true pressure. So one could go for a central flux where you just take the averages over the plus and minus elements. But then again, there are more in the literature, but for my solver, I just have the choice for pressure gradient as the pressure term as this. Then how to term for same thing for the velocity divergence term, you have the CG formulation, but then end up with this additional terms. The choice of U, again, same thing as for the pressure, just the average, or called as a central flux. So all this implemented, I just went for a well-known tutorial, flow past a dolphin. But So just we have examples in CG and DG, but yeah, and then wanted to compare it, yeah, both the methods. Um, since no don't really have a reference value to compare, just it was through visualization and just trying to get the L2 error. So now know all the terms that need to be treated. The diffusion term, so viscous, SIP method for the viscous term or the diffusion term, uh, Laux-Friedrich flux for the convective, and then the two that I mentioned now, and then the fractional theta scheme, which I mentioned earlier. And for the element pair, Taylor-Hood on each element. So space two, order two for velocity and order one for pressure. So nothing is concrete without a benchmark case, how the solver scales against a benchmark. So this should be Dr. Doken's favorite example, at least with CFD. So flow past a cylinder. Now the values are compared against feed flow, which is available on their database. So basically we have a 4+ cylinder, and then we would end up with a von Karman vortex treat. But then how does the values compare? Well, if I could just, yeah. So pretty well, good agreement with the reference values. This is for the drag coefficient, the variation of drag coefficient over time. And how does the lift coefficient vary? Um, Maybe I'll show you only the good parts. Yeah, but yeah, again, good agreement with the benchmark case. And yeah, the pressure difference between the left and the rightmost points on the cylinder. Again, uh, oh, looks good to me. Yeah. So, um, so yeah, there are more cases or examples that were solved, but I thought having the benchmark case would be a good concrete way of showing how the solver scales. So what I would like to do in the future is shift to FEniCS, and also inculcate MPI capabilities. And then, yeah, semi-linearize the convective term, because now we are solving the convective term is totally non-linear. One way would be to semi-linearize it, and then using a BDF form of order 2 or something. Then, yeah, immediately after all this turbulence modeling, using the variational multi-scale formulation, that would be the immediate next step. And then further have a ALE-based formulation for fluid structure interactions. And then, yeah, maybe far into the future, compressible Euler and compressible Navier-Stokes. Yeah, and I would like to thank the FEniCS founders, developers, contributors, everyone, and the forums, people who ask questions on forums. Well, this is a well-known, once a wise man, not once, but always says, please supply minimal. So all the forum discussions have been really useful. Um, and yeah, I'm open for collaborations. If anyone would like to understand the mathematical analysis done for the DG method, I have a report. If you would want, you could just ask me, where I've done existence, uniqueness, all the applied mathematics stuff, boundedness, coercity analysis, all those things. Yeah, and the code, most likely I'm looking for possibility of a publication. Maybe I do it after that. Yeah. Okay, that's it from my side.